Okay, sorry about that. Anyway, so back to the first problem. Okay, so I'm going to go over this again real quick. So our first problem was the unstretched to find k, right? So to find k, we simply made the free body diagram. I'm just going to go over this real quick. So we have the spring pulling up, which has a force of kx, and we have gravity pulling down, which is mg. So you just set those equal to each other because it's at rest, right? So there's no motion. So you have kx equals mg. Solve for k, you have k equals mg over x, and that's your formula for k. All right, so that's part one. And the k, yeah. So now we've solved for k. K was equal to mg over x. So now we need to find omega. Well, omega is given by the square root of k over n. But you need to be careful because this is angular frequency and we need just frequency. And so to get from angular frequency to normal frequency, we just need to divide by 2 pi. And so that will give us, let me write that out a little bit nicer. So omega equals the square root of k over m all over 2 pi. So that's problem 2. That's the formula for problem 2. So now we have, after t equals 0.37 seconds, what is the speed of the block? Okay, so this is where these equations over on the right here come into play. So this is your basic distance displacement formula for an oscillating anything. So in this case, we're starting from rest. This we're going to define as 0. So that's rest, and it starts with v naught equals whatever speed it. So in my problem, it's 4.9 meters per second downwards. That's what it says right here, downwards at 4.9. So whatever that is, it's given, right? So we have this initial velocity v naught. And so now the way we're going to do this is, well, to find, okay, so we have first x written out, okay? And the reason x is, so the amplitude, I'm just going to go through these real quick. It is an amplitude, that's easy. We don't know what the amplitude is, though. It isn't 0.1, right? This is 0.1, but this is not the amplitude because this is just the equilibrium position of the spring, but we don't know how far it'll actually go down now that we've pushed it with that initial velocity. We don't know how much energy that is. So this is our first formula. So we put a in, we don't know a though. The next term here is sine, right? And the reason we use sine and not cosine is because we're starting from 0. So if you guys think back to like trig, and you're looking at a wave, okay? If the wave starts at 0 here, then it's a sine wave. And if it starts at 1, it's a cosine wave, right? So that would look like this. Okay, so that's cosine. But if we look at our block here, it's if we graph this with respect to time, the block, as it bounces up and down, right? It's going to start here, it's going to go down, and then it's going to bounce up, and then it's going to bounce down, and it's going to bounce up, right? So this is a sine wave because it starts at the at our 0. It's technically a negative sine wave, but that negative will come in when we put in our v naught over here. So for right now, this is fine. But we could actually put this in here. So let's do that after all. So we'll put a negative here, and then we have a positive here, and a positive there. Okay. So let me think real quick. This might be wrong. The velocity in here needs to be negative. Anyway, we'll figure out the signs later. Right now, we're just going to be let's just focus on magnitudes first. So I'm just gonna ignore those for now. Okay, so we don't know A, so then our omega we found, that's over here, and our T is given as, here, 0.37 seconds. So basically what we need to do is we need to first find our A, and so what we're going to do is we were given V naught, so we have V naught equals A omega cosine of omega T, right? Well, omega T, we have those, right? T is given, omega we found this omega. We don't know the amplitude yet, but we were given V naught. So you just plug in those numbers. You plug in V naught, we got that. Plug in omega from over here, and that omega, and the T is also given. And the only unknown is going to be A then. So we can solve for A. So now that we found A, so A equals this, whatever. Now we can go back to this same equation, V equals, and now we can plug in the known A, known omega cosine of omega T, and now, actually, I'm sorry, in this problem, you don't use T 0.37, you use T at 0. So that means this whole thing will go to 0. And the reason we're doing that is because we're looking at initial velocity. So at time equals 0, what is happening? Well, we are given the initial velocity at time equals 0. But that means this goes to 0, which means this whole thing, cosine of 0, goes to 1. So technically, we just get A equals V naught over omega. And that's it. So now we can plug that into this equation. So this A, well, I'll just rewrite it. So V is going to be equal to V naught over omega times omega cosine omega T. And this T now is the 0.37 that we're given. These two omegas cancel. So we're actually just given that V equals V naught cosine of omega T. And so you guys can plug that in. Pretty straightforward. So now we have everything. We have A, we have omega. So let's look at, let's go to this. Okay. So we have everything. Now, what is the next question? It's probably going to ask for acceleration or displacement or something like that. So what is the magnitude of the maximum acceleration of the block? All right, so maximum acceleration will occur where? So this is an interesting problem. We have a constant acceleration from gravity down, right? And when we are at the bottom of the spring's extension, okay, so when this is fully extended, I'm going to draw a little picture over here. So, so when we're at the very bottom, this is the maximum stretch, right? We're going to have gravity still pulling down because gravity is constantly going to be pulling down, but we're also going to have the maximum force up. And that acceleration should be the same. So there's going to be no motion, right? But the force at that point is going to be this. It should be the same as when it's completely compressed at the top here. So you can try those, see if they're the same number, see if they're different. They should give you the same number, and the acceleration should be the same. So you guys can try that out on your own. But remember that when you're doing the force on this, you use the A that you found, but that amplitude is not quite the extension in this spring, right? Because our spring was already stretched 0.1 from the equilibrium, even just to begin with. So when you're doing the force on this, right, F equals kx for a spring. Well, this k is given, right? That's constant. This x is going to equal A, right, your amplitude, plus 0.1. And that's important to remember because otherwise your numbers are going to be off. So make sure you remember how far the spring was displaced at the very beginning of our problem, just by hanging the mass on it. All right, so that's that problem. Then we can go on. So at t equals 0.37, what's the magnitude of the net force on the block? Well, here we need to use our acceleration formula now. And you're like, oh, why are we doing that? Well, force is mass times acceleration, right? So we know A, we know omega, we know T, it's given. Find A, plug it in, easy peasy, no problems. So that's the formula you're going to use. And then just make sure that these accelerations make sense, right? So when you are below the equilibrium, right? So as soon as this block goes here, doesn't matter which direction it's moving, the acceleration is going to be up. And the reason for that is because the block is either first, so as it moves down, right, it's slowing down. So it gets here, and then it's here, and then it's here, right? And then it stops. And then it starts accelerating back up. Well, all that means is the acceleration was going up the whole time. The acceleration is trying to push the block back towards the equilibrium. And then once it goes above, right, so it's here, and then it's here, and then it's here. So now it's accelerating downwards. And so that's the important thing to remember here. So you can figure that out then. So like if you plug in a small t here, really very small, 0.001, right, this number, this acceleration needs to be positive. And so you can know that it's a positive here because of our drawing. And then we know that the velocity is actually going to be 0, and this is also 0. And so that should be your signs on those three equations. You guys can double check me on that. And so then where's the potential energy of the system the greatest? So it's actually going to be at the highest and lowest points. And that's because it says in the very beginning, the block oscillates on the spring without friction, okay? That means there's no loss of energy, which means it's a perfect system. So at all times, all of the energy will either be stored in potential energy due to gravity, which is mgh, or potential energy stored in the spring, which is 1/2 kx squared, or in kinetic energy, which is 1/2 mv squared. This is going to equal your total energy. And so it doesn't matter, So it doesn't matter, you're not losing any energy. But the thing is, this energy term here, this is not potential, this is kinetic. These two are potential energy terms. And so as long as the block is not moving, right, so if V is 0, then all of the energy will be in potential energy. And so where are the two places where the block isn't moving? Well, it's going to be at this top, right here, where it stops for a second, and down here where it stops for a second. And so that's why it's both of those options. The next problem is pretty similar. You have a mass on two springs oscillating back and forth instead of up and down this time. Effective spring constants, because as you push this block, say to the left, right, it's going to compress the spring on this side, but it's going to extend this one. And you would think maybe they're pushing against each other, but no. Both springs want to return the block to the center. And so basically, you can treat this as if you just had, so let me just clear this real quick. It's like you just have one big spring, right? So you have this is the drawing that they gave, this, and you have a spring here, and a spring there, right? But you could see this also just as this, where this is a much bigger spring, right? It's going to equal the exact same problem. So you can simplify to that. Period of oscillation, again, you need to be careful though. This is period, not, what is the other one asking for? It was asking for omega, right? Oscillation, it was asking for frequency,
One's asking for frequency, the other is asking for period. And frequency is in hertz, which is 1 over s. Period is in seconds, so you need to be careful which one you're solving for. How long does it take the block to return to the equilibrium for the first time? Well, you need to just find your period. And how long does it take to return to the equilibrium? Well, it's a sine wave, right? And so equilibrium, or maybe this is a cosine wave. I'm not sure how they do it, but let's say it's a sine wave, right? So we start here, we move, and boom, we're at equilibrium again. And so if our period is, say, 2 seconds, right, then it took 1 second to get to equilibrium. So now we have our time. We plug that into those 3 equations, acceleration, displacement, and velocity equations, and you can find how long. Well, this one would be displacement, so you just plug that in. Pretty easy. What is the speed of the block as it passes through the equilibrium position? Well, now we have the time, so you just put it into the velocity. And then what is the magnitude of the acceleration? Now we plug it into the acceleration one. That's the 3 formulas, just like in the last problem. Just make sure your signs are correct, and that's about it. Maybe you might have to switch around the sines and cosines. And I guess the important formulas for that are that there's displacement that equals whatever, a sine or cosine of omega t, and then v, velocity, is actually dx dt. Oh. So we rewrite that. So x, displacement. So that's sine or cosine, and this can be negative or positive. Velocity is actually equal to dx dt, and that's why the omega comes out. So it's like it's a chain rule. And then that would be negative. And then acceleration is dv dt. And so that's one way you can find out the signs. Those are some important things you can remember. What is the net force on the block at 0.89 seconds? A negative force is to the left, a positive force is to the right. So you need to first find where it is. So if your period is 2 seconds, right, and you have 0.89, that means it takes 2 seconds to go here, here, and back. So that's 1. That would be 2 seconds. So that means from here to here is 1 second, which means from here to here is 0.5. So it moves, as this block moves, it goes 0.5 seconds this way, 0.5, 0.5, 0.5, right? So 0.89 is a little under 1, right? So it'll move this way, and then it'll move back. And now you're taking a snapshot right here. So the forces are going to be pointing to the left because the spring wants to push it back to this position. And so then what is the net force? Well, you use acceleration, force equals mass times acceleration, just like in the last problem. And then what is the total energy stored? Well, you can look at it at whichever point you want. And that's the formula that I gave you actually on the last, this last thing. Here, it's, oh, well, except you don't have MGH. So it's just going to be a combination of 1/2 kx squared plus 1/2 1/2 mv squared equals 0. So what I would recommend is either taking it at x equals 0 or at x equals a. And so the reason for that is at x equals 0, right? So that's at this equilibrium position. This is x equals 0. This term will drop out, right? And the reason for that is, well, x is 0, so we just drop that out, and all of the energy is actually stored in the 1/2 mv squared in the kinetic energy portion. Now, so at x equals 0, 1/2 mv squared equals u total, right? Total energy. Or look at x equals a, because at x equals a, you're going to have 1/2 k a squared, and this term will drop out. Because at x equals a, that means this is pushed all the way over here, for instance, the block stops, and so you're not going to have any kinetic energy. It's all going to be potential spring energy. So I would pick one of those 2 points, and then you can just quickly find the total energy. Any other, total energy. If the block had been given an initial push, how would the period of oscillation change? So period of oscillation, if we go back to our formula, it's so that's only has to do with K over M, right? And what is K? Well, it's our spring constant. M is our mass. Neither of those change. So what's really interesting about springs is that it doesn't matter how far you're moving the spring, it'll always have the same oscillation frequency as long as your K is the same and your M is the same. So we can have a spring. So let's say we have a mass here, and we have a spring here, and here. Okay? And so if we're moving this block just in this range right here, or we're moving this block all the way to the edges here, it'll have the same frequency. So as it goes here, 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 it's going to be the same frequency as if we're going all the way over. The difference is that there's far more energy in this red line, because if it moves all the way over here, it has to have a much greater velocity, or the other way you can look at it is it's compressing the spring a lot farther. So the energy is far greater, but the oscillation frequency does not change. And so that's a fun fact, something to keep in mind when you're working with springs. Does not matter how much energy you put into it. What matters is how heavy the mass is and how stiff the springs are. So that's this homework. Shouldn't be too hard. It's really physics 1 stuff. They just want you to be able to do use those equations that I gave you, the trig functions, sine, cosine, that kind of stuff. So that should be it. Good luck, and I'll see you next week.